I decided to post this video in response to a request I got asking how to use a scope to fault find on vintage equipment. So we've got a scope here and a simple circuit setup. My first response to the query was, well, watch my video as I go through a lot of fault finding steps, because there is no single way to fault find on a piece of vintage equipment. It depends really on what the issue is you're looking for. Now, one thing I've mentioned quite a few times in my videos is that when I remove ICs from equipment when I suspect they're faulty, I try to remove them in such a way that I can fully test them. A lot of people just cut the legs off to make it easier to desolder. We don't learn very much doing that, so I actually want to know what the failure mode is for the devices, because fault finding on equipment like this is very much about experience, and I've done hundreds and hundreds of repairs on these machines. I've replaced thousands and thousands of ICs. Initially I was going to use the scope you normally see me using, and we will use that later in this video, to show the faults we're going to look at here. And I decided that was not necessarily that useful. A lot of people won't have a scope like that, so we'll start off with a cheaper scope. There are some limitations as to how cheap you can go with the scope. There are some very cheap scopes around that are quite useful if you're doing analog circuits, but the problem here is that we're looking at digital circuits, and you'll see a lot of comments online about, well, if you're looking at a 10 megahertz processor circuit, you need to be able to have at least a 10 megahertz signal. But it's not as simple as that. It's not really about the repetition rate of the signal. It's about the highest frequencies you're going to see in that signal. And in the case of a digital circuit, if we look at the scope on the left there, the rising and falling edges of those signals represent 5 nanosecond time durations. So you're looking there at well over 100 megahertz in terms of the frequencies that are present in that signal. Now, you might get a scope like this, and although it says 100 megahertz on the front of it, and this is a Siglent SDS 1104X-U, and it's a very nice scope. I purchased this recently. Actually, I purchased it specifically to make this video, and it is quite a nice scope. I was quite surprised when it turned up. The quality is nice. If you want me to do a review, leave a comment, but it's quite a nice scope, and it's kind of a minimum entry level for scopes, in my opinion. Like I said, although it says 100 megahertz, that is the claimed analog bandwidth. The actual bandwidth, captured bandwidth of that scope is about 20 megahertz, and that's kind of right at the bottom of what you really need in order to do this type of fault finding, because what you're looking for are small or potentially small timing errors down to maybe just a few nanoseconds. So I have tested this scope, and it does seem to meet the requirement. It's kind of at the bottom end, like I said, of what you would really need, but we'll go through, look at the issue here that we're going to see with various scopes. But just bear in mind as we go through, you don't need to spend a huge amount of money on scopes and test equipment, at least not to get started. Now, over the years I've picked up a lot of test equipment, and some of it's quite expensive, so what you normally see me using you don't really need. So for example, the scope you normally see me using has 4 of these probes attached, and these are the Croy probes. Each one of these probes costs more than this scope and all 4 probes that come with it, and of course there are 4 of these that I normally use, so that represents quite a big investment, and we'll see as we go through this video what difference this sort of thing makes. Now, ironically, the higher end scopes would be easier to use when you're starting out, because there's a lot of ambiguities in the signals you look at on a low-cost scope that are actually introduced because you're using a low-cost scope. So you need to try to filter that out and focus on the actual issues you're looking at. So what we've got here, and this is a circuit or type of circuit I use quite a lot for testing ICs. As I said, when I remove them from old machines, I try to remove them intact, and in fact all 5 of these ICs with labels on have come from an old machine. The 2 on the board are ICs that were causing issues. The other 3, the 2 labelled new, are new old stock devices, and the one labelled old good came from the same board as the ones labelled old, but it tests good. All 5 are 74LS02s, and they all test good in all of my test meters and all my digital testers. They all test good, but as I said, the 2 labelled old were causing faults in a machine I was trying to repair, and I'll try to demonstrate now why that is the case. So the circuit on the breadboard is this. Very simple circuit. We're feeding a clock in, and that's being fed from my Handtech HDG 6202B. Quite a nice signal generator, and one of the nice things with this signal generator is you can set the pulse width of the signal, but also you can set the leading and trailing rise and fall times. So I've got this set up to simulate what the spec sheet for these devices say the rise and fall times should be. So the circuit is a couple of NOR gates, and they're feeding into an XOR gate, and what this really does, it acts as a logic comparator, and if we get anything on the output, then it's because one of these is not behaving the way that it should. So with that said, what we'll do is start looking at the signals we're getting. I've got both old devices fitted to the board, and so what we have on the scope is the yellow trace is the clock going into the circuit that's fed from the signal generator. Channel 2 and channel 3, that's the purple and blue traces, are the output of the 2 NOR gates, and the 4th channel, the green channel, is the output of the last gate. Now, as you can see on the scope, we're not getting anything on the output. That's what we should be getting, and both of the intermediate signals, the purple and the blue, are showing the signal we would expect. And just to give you some context here, we've got this set to 20 nanoseconds per division. So you can see that the lag between the rising edge of the clock, the yellow trace, there's quite a lot of lag from that rising edge to when the devices switch, and that's what's causing the problem. Both are giving reasonable outputs. The outputs are a bit low, but they're still within the spec required to drive circuits further down the line, but there's a lot of delay from the clock rising edge to when the output of those gates changes. So this causes a lot of issues. You probably can't see it on the camera, but there's a lot of noise and jitter on the output, and this is typical of the sort of thing you're looking for with a scope. It's more evident on higher end scopes, but you can also do fault finding to a certain extent with a logic probe. So if we look at the output of this circuit, this is again the output pin, you'll see hopefully that it's just showing a low value. So it's just saying low, the signal output is low, which matches what the scope is saying. What I'm going to do now is replace one of these failing ICs with a new IC, at least a new old stock IC, ones that test good. So power off the circuit, swap the device, and we'll power back up. And if you look at the scope, notice now that the green trace, the output, is showing 2 very distinct pulses, and if we look at the output using the logic probe, notice it's also showing that the output is toggling. Now obviously if this was feeding a memory select circuit or a counter or something like that, then that would cause some major issues, and this is the sort of faults that you are going to encounter a lot if you work on vintage machines, and this sort of issue gets far worse the more complex the machine becomes. So you start getting rogue signals like this, and all bets are off. Normally it manifests itself as the machine won't boot at all, or it randomly fails and crashes, or memory test functions they return random failures. Quite often they will return a failure of the same address each time, because it's possible there's some variation in the way the memory devices work, or memory buffers work. There's a whole range of things that can affect this, but in general, if you change an IC and things change, then something is wrong. There are instances where certain designs require certain manufacturing types, but it's for this type of reason. Now normally if you fit a new IC and the machine, in this case it might have been running but with the occasional issue, and you put a new IC in and then it fails to work at all, you might be tempted to think the new device is faulty. But what we'll do now is, rather than swapping the new device out and putting the original back, we'll try putting a new device in the second location. So all the same type, remember, just different performance levels. Turn this back on, notice the problem has gone away. But also notice, again, I don't know if you can see it, you might be able to see it later on with the more expensive scopes, but also notice a lot of the noise and jitter has disappeared as well. Now, very simple circuit, but if I add a 22 picofarad capacitor to this, so I'm going to add this to one of the signal lines going into the final gate. Notice it doesn't make a lot of difference to the signal. However, if we swap one of the devices back to the old type, if you look at the green trace, I'll remove the capacitor, and notice how it makes quite a bit of difference to the signal. So bus loading, the layout of the board, adjacent components, the fan out, all those things can have a major bearing on this, but it's nothing to do with the repetition rate of the signal. In fact, what we'll do here is we'll change that. It's currently 1 megahertz. We'll go up to 2, so 2 megahertz, 3. So notice it's having no bearing whatsoever on the fault. This is about the rate of change of the signal being fed into these ICs, and not the repetition rate. We can also change the pulse width, and similar, although the pulse is getting wider, you can see that the anomalous signals are staying the same. They're just moving position, but they shouldn't be there at all. So finally, although the new ones are new old stock, what I do have is a known or tested good device from the same board, so we'll try fitting that, and once again the issue has gone away. So it can be a bit confusing, and as I said, this gets far worse the more complex the circuits become. So if you fit a new device and things change, you may be on the right track. It might be the fault's in a completely different part of the system, but the fact that something has changed means that you've probably got an issue somewhere with one of the devices starting to fail. The other thing to bear in mind is capacitors on boards do often fail, and I've got a capacitor here. If I remove it, notice that the signals change. Still not too bad, but if we go back to one of the older devices, so if you look at the green trace, you hopefully can see there are a lot of spurious signals that come and go, but if we put the cap back in, they disappear. So what we'll do now is replace this scope with the scope I normally use. So again, it's a 100 megahertz scope, but it's a higher cost scope. And in fact, before we do that, what I'll do is I'll swap the probes for more expensive probes, because the probes themselves do make quite a bit of difference. So I'll get all these swapped out and we'll see how the signals then look. So I've swapped out the probes, and superficially the signals look fairly similar. The edges are cleaner, of course. The response of these probes is much better. But one thing we can now clearly see that we couldn't really see before is the a jitter on the rising edge of the output signal, and again that can cause a lot of issues if this circuit was being used, for example, to feed a counter or a memory select circuit. So straight away, by using the more expensive probes, we can see more. We could kind of see it with the cheaper probes, but it's the sort of thing you're looking for and something you do have to be able to spot if you're using a low-end probe, low-end probes and a low-end scope. You can do it, and as you can see, it works just fine, and so you don't need to throw lots and lots of money at a very expensive scope. Of course, the more you spend, the better the performance, but what I'm hoping you can see here is that we can quite easily detect this fault with this scope. And you can also see the skew in the timing between the purple and the blue trace. The blue trace is clearly much slower, and that's the IC that's labelled old, and that's what's causing these spurious signals. It's the delay between these two signals, which is on the trailing edge, it's best part of 30-35 nanoseconds, which might not sound like a lot, but in digital IC terms it's very significant, and it does cause a lot of problems. And the board in question didn't appear to have been abused. It was just the age of the devices, and this also varies between manufacturers as well. And one thing we'll do before we go any further is I'll just try changing the supply voltage. So we're at 5 volts, I'll go up to 5.2, and notice it doesn't really have that much impact. So if changing the supply voltage makes a big difference, then chances are it's a different thing you're looking for, a different type of fault, because normally this kind of situation is not vastly changed by increasing the supply voltage. But if we go down, I'll go down to 4.8 volts. Again, you can see that all that really happens is the amplitude changes, everything else stays the same. So, like I said, if changing the supply voltage makes very little difference, then chances are this might be the type of thing that you're looking for. If it makes a big difference, then most likely you need to be looking for a different type of fault. And I'll swap this scope out with the one I normally use, and we'll see if we can pick up any more information. Okay, with this scope you can clearly see far more information. The signals are a lot clearer, and the scope clearly has a much better bandwidth, and more importantly, the this jitter that we were seeing fairly vaguely before is now very clear, and the information we can get from this is obviously far clearer. We can see the relative timing much more clearly, and it makes life a lot easier. Having said that, we could still see these issues with the other scope. So what I'll do now is, just to show the difference, is this is a 100 megahertz scope, but it's a true 100 megahertz scope. We can capture signals at 100 megahertz. We'll now replace this with a 500 megahertz scope and see what the difference is. We'll just look at the input and output signals and see if we can determine any difference using a much faster scope. So using the 500 megahertz scope, you can clearly see much more information. The runt pulses are much clearer. If we did a single capture on the runt pulse, we'll be able to see it in detail. But also the rising and falling edges now have the correct time. They were lagging behind a little bit in the previous two scopes, but now they do have the correct rise time. So again, although we don't need a scope of this speed for this particular fault finding, you can see that as we go up the scale in terms of scope performance, that we do get more information. You don't really need to go this high, so the lower cost scope is perfectly adequate for basic fault finding. The last scope we'll look at is my LaCroix. Incidentally, this is a Tektronix TDS 3052. We'll look at my LaCroix scope, which is the most expensive scope I have. I do have a 6 gigahertz scope, but we won't look at that because that's not something you'll see that often. The LaCroix were fairly popular, and it is a high-end scope. I think it cost £163,000 when it was new, and that was about 25 years ago. Most of that was software options. I needed it at the time for some development I was doing, but we'll see the difference between that scope and the scopes we've looked at so far. The Tektronix scopes were also very expensive. I think they were something like £3,800 when they were new, but these days you can pick them up for a fairly reasonable price. But I'll get this hooked up to the LaCroix. I can't get the LaCroix down onto the bench here, it's too big, so I will have to try and move the camera, and we'll see these same signals on the screen. So looking at the LaCroix scope, and this is a Waverunner 6050 by the way, and it's a 500 megahertz scope, but it's a 5 gigasamples per second scope, unlike the 1 gigasample per second scope I normally use, which is only a 100 megahertz scope. So very fast capture on this scope, and you can clearly see that in the data we're getting. Far more information in this. We can measure down to picoseconds on this scope. You don't normally need to do that. It's a nice feature to have if you're doing certain types of work, but you certainly don't need to spend this amount of money on a scope to do fault finding on vintage computers. But I thought you might find it interesting to see the difference in the quality of the signals that you can capture. Again, they're much better quality signals, and we're looking now mostly at the actual circuit noise rather than the system noise of our test equipment. So what we'll do now is look at the same signals using the logic analyzer. Looking at the logic analyzer, I've got this set up with the same 4 inputs. They're color coded the same. So the top one is the clock, gate 1 and gate 2 outputs, and then at the bottom we have the output of the entire circuit. So we'll start this running. It's all running. I've got 2 new ICs fitted, so we shouldn't see any problems. We'll start this running, and we've captured some data. Let's zoom in a little bit there. And as you can see, we're getting good output. There's a bit of a delay at the start. Let's zoom in on that a little bit, and you can see we've got a bit of a delay here, just a few nanoseconds, but other than that these signals are looking good. So what I'll do now is swap the IC, or one of the ICs, with one of the old type ICs, the ones that are starting to fail. Power the circuit back up, and we'll do another capture. Remember, the bottom green trace is the output of the circuit, so we'll do a capture, and notice now that we are getting a similar effect, along with some odd behavior in the middle. So the blue trace is the output of the failing gate, and the green trace is the output of the circuit, and you can see that clearly we're getting an issue here. These 2 pulses shouldn't be here, this one shouldn't be here, and you can see even the logic analyzer can pick this up. I should point out here, there is a word of caution using a logic analyzer like this. If we go to the setup, I've got this running in timing mode, capturing at 2.5 nanosecond intervals. If we go to state mode and we capture using the clock, and now we try to do another capture, I'll zoom back out so we can see the entire signal. So notice that it's behaving perfectly. We're not getting an issue. It's actually this part of the signal we are interested in. You can see it appears to be fine. We're not seeing anything on the output, and that's the disadvantage using state analysis mode of a logic analyzer, because the capture is only updated on the clock edges, and I've got this set to capture on both clock edges, rising and falling, but we're not seeing the rogue output simply because it's only capturing data when the clock edges occur. If we go back to timing mode, we've got 2.5 nanosecond capture set, and we do another capture. I haven't changed anything else. Let's get those back on the center of the signal. Once again, you can see that the rogue signals have reappeared. So using a logic analyzer can also be a good tool in this type of fault finding, although you do need to have a much better idea as to what you're looking for and make absolutely certain you've got your logic analyzer set up correctly. Otherwise you might end up seeing data or rogue data that's more to do with the analyzer setup rather than the actual circuit faults. So you might be wondering, well, does all this really matter? Does it have any real impact on the circuits in question? And the answer is absolutely yes. So what we'll do now is have a look at a practical example of this. I'm going to introduce a timing fault in the Z80 computer project, and we'll see how small timing issues can have a big impact on the operation of a system. So I've got the Z80 computer project on the bench here, as you can see, and it's working fine. If we try to run any commands, it's all working the way it should. I'll reset it so you can see the startup logo, and it's all behaving perfectly. What I'm going to do is swap one of the ICs on this board with the IC labelled old, or one of the ICs that were labelled old, so these are the failing ones. Still test good in all my digital IC testers, but it was the source of an issue on a vintage machine I was working on. So I'll get this swapped out, and then we'll boot the computer back up and see what effect this has. So I've got the IC swapped out. Again, it's 74LSO2, and this is in the decoding circuit for the video output. So we'll try powering this back up. I'll turn the lights off so you can see the screen a bit better. And hopefully you can see that something's not quite right. So I'll try resetting. Now the machine is running. If I go to the monitor, hopefully you can see that we're actually getting the monitor itself, and it's all the text we would expect is coming out. But there's also a lot of noise and mess on the screen. Let's turn one of these lights back on so you can see the machine a bit better. So clearly something's wrong with this, and again I'll try clearing the screen, and apart from the rogue character in the middle, it seems to be doing what it should. But when we try sending actual text to the screen, we're clearly getting a problem. Now this is caused by the timing of the signals going to the SRAM. So although it's writing to the correct address, the write enable line is staying low for too long. It's staying selected for too long. So after the multiplexers that supply the address to the SRAM have really changed back to the next address, that line, the write enable line, is still staying asserted for, it's only about 3 or 4 nanoseconds longer than it should. But what's happening there is that the value, so for any one of these characters we're trying to write, it's actually been written to 2 locations. It's been written to the correct location, and then when the memory changes while the SRAM is still write enabled, then a second address is being written to. So all these characters somewhere will appear in this text, but it's putting them in more than one location at once. And that's why when we clear the screen, the only character we get on the screen apart from the correct cursor is the cursor character again, but in a different address. And the address, the rogue address, will vary each time we do this because it's going to be dependent on the address on the main address bus of the Z80. So if I clear again, for example, the rogue character moves around. So that's caused by a timing skew, a timing error caused by a failing IC. The IC is working, but it's not working the way that it should. It's just too slow. So I'll swap the IC back to the working one and we'll see if that fixes our problem. Okay, I've got the working IC back in there. As I said, they're both working, but the new working IC, the one that actually meets the specification. Turn the computer back on. And the fault has gone away. We're getting this NV checksum fail now because while it was writing to rogue addresses, it would have overwritten some of the values in the non-volatile RAM. So then when it booted back up and ran the self-test, it realised that the checksum in the NV RAM no longer matched the contents. But you can see now that it's working as it should. So although the IC tested fine in the digital IC testers, when we put it into an actual machine, it causes problems. And this is the sort of problem it's kind of tricky to track down, but if you know what you're looking for, then it's fairly easy to find. What you have to do is look at each device in turn, try and figure out, generally speaking, where in the system the error lies. In this case we were getting errors with the video RAM. So then start looking at the timing of the signals going to the video SRAM, for example. If that doesn't uncover anything, then just work your way back from there to the Z80. So generally it's fairly easy to find faults like this, but just be warned, it's not necessarily the case of a totally failed device. And also you might find when you put a new device in somewhere, the system behaves differently. It doesn't fix the problem, might even make problems worse or introduce new problems. And that's why fixing these old machines can sometimes be a bit of a sleigh ride, because you change one thing and then something else seems to stop working. It's not necessarily because you've broken something, it might just be because there are multiple ICs that are starting to fail, and when you change one device it kind of snowballs and has a knock-on effect, and you need to start looking into other faults, but you do need to fix them all. And there's no point just putting the old IC back in because it seems to work better. That might just be masking a problem that manifests itself in numerous other locations. So it's all part of the game. It's quite good fun tracking these sorts of faults down, but just be warned, you're not necessarily looking for failed devices, and in fact in about 90% of the repairs I do, the devices still test good in the IC testers, but they fail in the actual circuits. Okay, so that's it for this video. If you want to see more of this sort of depth of fault finding, then please leave a comment. Normally I skip over this type of thing because I think a lot of people find it fairly tedious, but if you want to see more of this, then let me know.